Okay, now we're going to look at an application of this called exponential growth. So in this setting, we're going to be thinking of like a population or an amount of money looked at over time. So our input is going to be t, little t for time. Okay. And it's very common for it to be expressed in the following format. So our function is going to have this exponential p naught times b to the time over a t, capital T. If we take a look at this, p at 0 is going to be equal to this p naught b to the 0 over capital T, or p naught b to the 0, which is the same thing just as p naught. So p naught is the symbol we use for our starting value. So this is the starting amount of our population. We also call this the initial amount. Okay. And so we know that every exponential function that looks like just b to the x is going to go through the 0.01. All we're doing here is taking our exponential function and just stretching it so that its initial condition is equal to p naught instead of 1. Okay. What else are we doing here? The base is b. This is also sometimes called the growth factor. And it's very common to express this in the form 1 plus a number r. And the number r will be called the growth rate for reasons that will become clear like super soon. Capital T here is called our time step. So it's very frequent that we're frequently given a rate in terms of a time, a rate of growth in a time. So for example, when we were looking at the bacterium example, we said every 20 minutes our population doubles. So there, our time step would have been 20 minutes. Okay. If we take a look at our population at this time step, we get p naught b to the t over t, or p naught times b. And to say what this growth rate means, we can say that the percent change we can look at by saying what is the final value minus the initial value over our initial value. Okay. If we look at our percent change in one time step, we have p naught b minus p naught over our initial value of p naught, okay, which gives us just b minus 1, or what's called our rate, r. Okay, and so this is going to say how much our population is changing in one time step. Okay, so let's take a quick look at a couple of examples of this, and then we'll look at this in the context of money. Okay, so imagine that we have some wolf population that is growing exponentially, and in 2011 we have 129 wolves, and in 2013 we have 236 wolves. We'd like to write an equation that represents our population of wolves over time. Okay, so let's just write down some of the information we have. let's set our initial time to be equal to 2011. So our P of T is going to be our wolf population. T years after 2011. So that means that our population at time 0, which is our P naught, is equal to 129. All right, so we can write P of T then is equal to 129. And we can take B to the time. Okay. So our goal is going to be to figure out what is this base B. So we know that 2 years after 2011, in 2013, P of T2 is going to be equal to 236. And this is also equal to 129 B to the 2. Okay. Well, that lets us figure out what B is, because we can divide 236 by 129. And this is equal to B squared. And so B is just going to be the square root of this. Okay, and so we can write our population at time t was equal to 129 times the square root of 236 over 129 to the tth power. All right. Let's take a look at another example. Here, our population is growing with a growth rate of 12%, and we have an initial value of 30. We'd like to write an exponential function for this function. Okay, so here our growth rate is 12%. So we are going to use that P of T is equal to P naught times this 1 plus R to the T. All right, our initial value was equal to 30, and our growth rate was equal to 0.12 T. And so this gives us 30 times 1.12 to the T. Great.